So welcome back, everybody. Last time I had stopped the discussion of Russell's paradox. Um, so as I said last time, this was supposedly discovered by Bertrand Russell as his giant tome, which was named Principia Mathematica, named after Newton's famous work. Which, like Newton's attempt to put, all of physics on new footing, Principia Mathematica was supposed to put mathematics on new foundation. So the goal of Principia Mathematica was for Bertrand Russell. So Bertrand Russell and I believe Whitehead was the other mathematician. Their goal was to basically put mathematics on solid logical footing in kind of the same way. And so they had this massive tome. I can't remember exactly how long it is, but it's a really, really big work. Supposedly putting, math on solid logical footing. And as it was going to printing, Russell thought about this paradox, which kind of destroys all of what they had worked on in the book, which is the following. So, as I said last time, so if I let S be the set of all sets, such that maybe I should just say the set of all sets that do not contain themselves. Okay. And we do this in a way that, so S is a set of all sets that do not contain themselves, and so a set is an element of S if and only if it doesn't contain itself. Okay, and all such sets belong to S. Okay, so S has all of them. And then the question is, does S contain itself? Okay. So before you get too caught up in maybe whether or not we're doing some kind of like language trickery, and you think that maybe this isn't like a legitimate construction from that angle. One of the examples I gave last time is the Barber paradox, which is basically an informal way of coming up with this exact same thing. This could also be stated, purely logically. Like I could state this in symbols, right, uh, without any logic whatsoever. So or without any words whatsoever. So if S is defined to be, say, the set of all X, such that X is not contained in X, then S being contained in itself, right? This occurs exactly when or if and only if it is not contained in itself. This is a contradiction. You can't have both of these. Something can't be contained in itself and simultaneously not contained in itself. Right? So this is the problem. So, the informal examples of where this could occur is my example from before, that you have a barber that is male, and the barber shaves every man in the village that doesn't shave themselves, right? And so the question is, who shaves the barber, right? Now you have to state it so that not only does the barber shave every man that doesn't shave themselves, he only shaves those men that do not shave themselves. So if you get shaved by the barber, then you don't shave yourself. That's the defining principle. So then the question is, who shaves the barber? Well, there's only two options, right? He either shaves himself or he doesn't. But if he shaves himself, then he doesn't shave himself, because he only shaves men that don't shave themselves. So if he shaves himself, then he doesn't shave himself. And if he doesn't shave himself, well, then he has to shave himself, because he shaves exactly those men that shave themselves, or that do not shave themselves. So So if he doesn't shave himself, he has to shave himself. So it's an informal way of saying kind of the exact same situation. When is the final for the class? Let me type this in chat so that it's not lost in the. Actually, when is I think the day of the final? Let me look up. There's a schedule for. I'm gonna have to go to the math. Let's see here. University Standard Final Exam Schedule. So this class it's Math 274, so I don't think it follows the common final exam schedule. Oh, actually it does. Oh, I didn't know that. Yep, 274 is the last math class that follows a common final exam schedule, which means it's on the first day of finals, but you don't have to worry too much about that. I will post it soon. I will post it like later today, and you will have a window to complete it. So the window is the exam itself is scheduled officially from 1:30 to 3:30, but you're not going to have that. You're going to have longer than that. So the exam won't take you longer than that 2-hour window, so you will have that 2-hour window to do it. And like I said, the exam won't take you longer than 2 hours, but you'll have longer than that to do it. So let me. So it's on May 13th, 1:30 to 3:30 is the official time, but you will have access to the exam for at least, say, 3 or 4 days. So you will have till after that, but you will have that window at least where you have access to it, and actually doing the exam won't take longer than that. So yeah. Anyway, that's the deal. So I'll make an announcement on that. I'll post an Elms announcement on that later. Yeah. Okay. So anyway, another example of Russell's paradox that's kind of more concrete is there's an example about so Wikipedia has a really funny example about lists of articles. So they give a list of encyclopedia entries within the same encyclopedia. So they have 5 lists, like a list of articles about people. So then they have like a list of articles about random people. A list of articles starting with the letter L. So there's a whole list of articles starting with the letter L. A list of articles about places. Okay. List of articles about Japan. Okay. And then list of all lists that do not contain themselves. And then the question is, does the list of all lists that do not contain themselves contain itself? Right? Because if it contains itself, then it doesn't belong to itself, and then it should be removed. But if it doesn't list itself, then it should be added to its own list, and so then it does list itself. Right? So now you could attempt to resolve those applied versions, either the Barber paradox or that thing, the example I mentioned with the list. You can attempt to resolve those just by saying, oh, well, clearly, like, that Barber doesn't exist, or the list doesn't exist, and that solves it, right? That something like that doesn't exist. The reason why Russell's paradox is a paradox is that this set must exist, according to what's called naive set theory now. So, at the time, what we now call naive set theory is basically, that was it. That was the only set theory that was known. So according to naive set theory, which is what it was called, okay, that was the only set theory at the time, but according to naive set theory, S must exist. So this is a problem. And this is a problem because it's a true paradox, right? It is a true paradox. A lot of times, paradox is used to to describe a situation that seems extremely unintuitive or seems like it shouldn't be true, but it's actually true. So, for instance, we're going to talk in a little bit. About something called the Banach-Tarski paradox, which is not actually a paradox. It's just a really weird thing that's true. And so a lot of times that when you hear paradox, like the twin paradox, right, in relativity, it's not actually a paradox. It is just a weird true statement, right? But in this case, this is literally a paradox in that you have S is contained in S and S is not contained in S. These are simultaneously true, and that just can't be, right? This goes against like the founding principles of first order logic, right? So this is no good. And so there must be something wrong with what's called naive set theory that allows for this. And it's really something with set builder notation is so nice. It allows us to describe sets in a really, really nice, convenient way. But there's like something inherently wrong with it that you're not allowed to put some sets together in this way. Okay, but it would take a lot of hard work to actually show what the problem was. So two mathematicians who did a ton of work in doing this were Ernst Zermelo, a German mathematician, and Abraham Frankel, who's a German-Israeli mathematician. And let me get there. So Ernst Zermelo lived, he was born in 1871, died in 1953. And Frankel was born in 1891 and died in 1965. So these two mathematicians came up with now what is called Zermelo-Frankel set theory. Okay. And this is the foundation of the math that you are used to. So the math that you have encountered, the solid footing that it is on at its foundation is this. You'll see this abbreviation a lot. So Zermelo-Frankel theory set theory plus something they didn't explicitly include, which is called the axiom of choice. The axiom of choice is an axiom, right, in the same way that you had axioms for Euclidean geometry or some basic axioms, say, of groups or fields or rings for these are objects in math that have axioms that define how they work. So, for instance, if you have a mathematical set that has an operation on it that we can think of as multiplication, if A times B is equal to B times A for every element, then that satisfies what's called the commutativity axiom for multiplication, right? So the axiom of choice is another axiom. And it has to be added in. It is something that mathematicians did a lot of the times kind of without assuming that it was an extra thing, but it is indeed an extra thing. I'm not even going to state it. But Zermelo-Frankel set theory plus axiom of choice, this is called ZFC sometimes, so ZFC set theory. And this is the foundation of all of the math that you've encountered. Okay. Now, can you do other sorts of math, say, based on some other underlying axioms? Absolutely. And if you're interested in that kind of question, then you should investigate logic or foundations of math stuff. So that's where that heads, basically. So questions like what happens if you have a math without the axiom of choice. Now, the axiom of choice is something that if I stated it to you, you would think is maybe pretty innocuous. It has to do basically with it has to do with the existence of what's called a choice function. That is not immediately apparent that it mentions anything about a choice function, because actually the axiom of choice is equivalent to the statement that every Cartesian product of a collection of non-empty sets is non-empty. So every Cartesian product of a collection of non-empty sets is non-empty. This is one way of stating the axiom of choice. Okay. Now, what's a Cartesian product? So if I have a set, so for instance, if I have the set that's the real number, so this is the reals, we'll say, then the Cartesian product, R cross R, this is the Cartesian product of R with itself. We write that as R2, right? Or R squared, but usually we just say it's R2. This is the plane, right? So it's the collection of all ordered pairs, right? XY, where X is in R and Y is in R. So you're familiar with that. And of course we could form the Cartesian product R cross R cross R, which we know as R3, which is the collection of all ordered triples, X, Y, Z. Okay, such that X is in R, Y is in R, Z is in R. Now, this is where you've seen Cartesian products before, but we can do this for any set. So if I have three sets, A, B, and C, I can consider the Cartesian product A cross B cross C, which is, again, the collection of all triples. Instead of writing X, Y, Z here, I'm going to write A, B, C, where A is in A, B is in B, and C is in C. Now, if this is a finite Cartesian product, then this statement is trivial. It's just true, and it's easy to see that if each of these is a non-empty set, right? So a set can be empty. That's just a set that has no elements in it, right? So if each of these is non-empty, if each of these has at least one element in it, then this Cartesian product itself has at least one element in it, so it's non-empty. Okay, and so the axiom of choice is not needed when this is finite. But what happens if this is an infinite product? So this is, we'll call it A sub 1 cross A sub 2 cross A sub 3, and so on. Cross will go out to some A sub n, but then we keep going. We don't stop, right? A sub n plus 1. And then we keep going forever. This is an infinite product, right? Well, now the question of whether or not this is non-empty is, even if all of the sets themselves are non-empty, is a little less obvious. And it is a little less obvious because this product could be even worse. It could be like it could be an uncountable collection of sets. So I mentioned last time that, the reals, for instance, are an example of an uncountable set. Well, imagine you had, the same number of sets listed here as there are real numbers, right? So you can think of these sets, instead of being indexed, right, by the natural numbers, 1, 2, 3, 4, up to n plus 5, and so on. Instead of being indexed like that, they were indexed by like real numbers, right? That's how many of them there were. So imagine you had an even bigger collection, right? Is this statement still true? Well, the answer is you have to assume it. There's no way to show it. It has to be an axiom that you toss in. Okay, and so the axiom of choice is included in the set theory that you've been doing as part of math your entire math career. Okay, but when the axiom of choice was first brought in, or first really laid out by mathematicians, it faced a huge amount of opposition. And you might say, why? Like, why would they think the axiom of choice is bad? So, one thing that is great from the axiom of choice is the axiom of choice. So, axiom of choice is equivalent to many amazing statements. Okay. So one, every vector space has a basis. So if you assume the axiom of choice is part of your set theory, then a statement that is equivalent to that is that every vector space has a basis. Okay. Another statement that is related is Tikhonov's theorem, which has to do with Cartesian products of compact sets. So a Cartesian product, this is what Tikhonov's theorem says, a Cartesian product of compact sets, this is a topological thing, is compact. And this is usually taken as like the most important theorem in all of classical general topology. Okay, this is a theorem in topology. And this is a very, it might not be, if you've never heard a definition of compactness, or you don't maybe know what the definition is. The definition of compactness technically is kind of complicated, but the way to understand this is in the reals, we have something called the Heine-Borel theorem, which says that a compact set, if it's a subset of the real numbers, is a closed and bounded set. And so you know, for instance, that coming from calculus, closed and bounded sets were super important because a continuous function was guaranteed to have both a maximum and a minimum on a closed and bounded set. This is called the max-min theorem. And so restating that in terms of compactness using the Heine-Borel theorem is that basically a function, a continuous function on a compact set has a min and a max. Okay, so compact sets are extremely important. It's one of the most important conditions that a set can have, even in calculus. But this is a topological condition. Okay, this is actually a factor of property coming from topology. Okay, so it's equivalent to those two. At least it's equivalent to a lot more. The existence of non-measurable sets. Okay. Now, what is a non-measurable set? Okay. So I mentioned previously that after the work that Riemann did in integrals, putting integrals on completely solid footing, the state of integration was that of what was called the Riemann integral. So this was improved by Lebesgue in the early 1900s. And so French mathematician Lebesgue came up with Lebesgue integration. And Lebesgue integration required, so eventually as that would be worked out, Lebesgue integration was integration done on measurable sets. So Lebesgue integration takes place on measurable sets, as they were called. So I'm not going to get into a definition of what a measurable set is. Okay, but it seems to be an entirely reasonable definition. And every set is measurable without the axiom of choice. Okay, but with the axiom of choice, it is possible to construct non-measurable sets. Now you might say, well, this is kind of an argument for not including the axiom of choice, right? We got two really nice statements or theorems from it, but this seems like a less nice thing. This is like the existence of bad things comes from the axiom of choice, and that's true in a way, that tossing in the axiom of choice gives you some bad stuff. It also gives you something that you might view as extremely strange, which is the Banach-Tarski paradox. What is the Banach-Tarski paradox? Sometimes people call it the pea in the sun paradox. It is the idea that you can start with, say, a ball. Okay. You can split it up into pieces. Maybe there's another splitting. You could take those pieces after you've split them, after you've cut them. Okay, you can actually do this in as little as 5 pieces, I think. So, like the most efficient way that you can cut this is you can cut this into 5 pieces. You take those pieces, and all you do is you move them apart. You translate them, you can rotate them, you can do those things, but there's no like stretching, tearing, anything like that. You can just take those pieces and reassemble them. Okay, reassemble them in some way. Okay, you can reassemble them into 2 balls of the same size that you started with. Okay. So you can reassemble 2 balls or you can reassemble 1 ball into 2 of the exact same size. Okay. Now, this seems like clearly impossible to do, right? You have literally somehow you started with some amount of material and you've doubled the amount of material here. So how does this work? The trick here is it's not some geometric trick that's going on. What is happening is the weirdness of non-measurable sets is such that because of the axiom of choice, you can cut these things along. You can use a non-measurable set basically to define the cutting. Okay, and the weirdness of these non-measurable sets is such that you can do this crazy process to reassemble and literally double, the ball that you started with. Okay. Now, this is possible. Again, it's a paradox in quotes because it's not a paradox. This is a thing that you can do. You can do this with the axiom of choice. Okay. And so the Banach-Tarski theorem doesn't exist without the axiom of choice because it's required to be able to construct these what are called non-measurable sets. Okay. So it's a bit of a conundrum because you can either choose to have the axiom of choice and you get some very nice facts. There's too many to list here. There's actually a ridiculously long list of things that are equivalent to the axiom of choice. And many of them are very, very nice, and many of them are very innocuous. It would be very strange if if it wasn't the case, right? So without the axiom of choice, there would exist vector spaces, for instance, that don't have a basis, right, or something like that. But you also, it's not cost-free. You get some weirdness popping up, okay, due to the axiom of choice. Okay, and so ZFC puts us on solid footing. But how does ZFC address the Russell's paradox? So how does ZFC address Russell's paradox? How does it solve this problem? Well, it would say that you can't construct that set. So that set S is not constructible. So that set S is not allowed or is not a valid construction under the axioms of ZFC. Okay. And so under the axioms of ZFC, talking about things like the set of all sets, right? So things like the set of all sets, or the like collection of all collections, however you want to word this. The set of all spaces satisfying certain axioms. These things are not valid. Okay, so these are not valid constructions under ZFC. Now, a problem with this is that sometimes you very much want to talk about objects that are like the set of all sets, the collection of all collections, the set of all spaces. You actually want to talk about these. Okay, so in fact, let's go to topology for a second to understand why we want to talk about these things. So in topology, what is the study of a topological space? So a topological space that we'll call T. So a topological space T is two objects. Okay, a set that we'll call X and a topology, we'll call it script T. Okay, and so the topological space together is the underlying set X, and then there's a topology on X we'll call, say, script T. Oh, this went the wrong way. I haven't written a cursive T in a while, I guess. That's weird. My first letter of my name is T, and I sign my name all the time. What's going on with that? Okay. So anyway, this is a topological space. So it's a set together with a topology. And we very much want to talk about in topology. I'm not going to define what a topology is. It is okay. I will. I won't define it totally. I'll just say it's a collection of open sets. Open sets of X. Now we define what the open sets are. So the sets in the topology are what we call the open sets, and they have to satisfy a list of axioms. They have to satisfy a few axioms. And if they do, they're called a topology on that set. And if you take the set together with a topology on it, it's called a topological space. Okay, and so notice that if I wanted to talk about the set of all topological spaces, okay, what's the problem? Well, a topological space is actually more complicated than just a set. Because a topological space is a set and this other thing, a collection of open sets of the set, right? So this is an even bigger set than the set of all sets, right? So this is really, what this is equal to is the set of all sets X and topologies T on X. Right, is what this is. So this is bigger than the set of all sets. This is like the set of all sets plus some other stuff. Okay, but we want to talk about this. Okay, we want to talk about this. I won't give any more further motivation than that, but in topology and in some related areas, we actually want to talk about things like the set of all topological spaces, the set of which includes the set of all sets. But Zermelo-Fraenkel set theory is ZFC is the foundation that we're all on. So how do I do that, right? It says we can't talk about these. And so basically the idea is we have to address the word set, and we have to dance around it a little bit, okay? We have to dance around it. So the second we say a word set, under ZFC, that has some things that it has to satisfy that prevents us from being able to build, say, the set of all sets. Okay, and so what we do instead is we talk about classes. So instead of sets, we investigate classes, which might be seen like we're doing kind of a little semantic trick, but the idea is that we can actually rigorously define the difference between these two. Sometimes a class is a set, but sometimes it's not. Okay, so that's the key point. So key point is sometimes a class is not a set. So, for instance, the class of all real numbers, between 0 and 1, right? That is a set. That's just, the open, well, whether I included the endpoints or not, it's either the open or closed interval from 0 to 1. Okay, so that class is a set. But there are classes I can describe, like the class of all sets, that's not a set, right? Because under ZFC, the set of all sets is not a thing. We can't construct it. And so sometimes a class is not a set. Okay, so we investigate classes. This leads us to something I've mentioned previously, which is known as category theory. Okay. And so we discuss categories, which are examples of classes. So a category is we'll say a class of objects, right? So it's a labeled directed graph. Okay, so it is a labeled directed graph involving objects as the nodes and morphisms as the arrows. Okay, so for instance, maybe I have objects A, B, and C, and then I have arrows between them. Right, so here's another arrow, here's an arrow. And so if this morphism from A to B is labeled F, and this morphism from B to C is labeled G, then maybe this arrow that I've drawn is the morphism that is G composed with F, right? It's the G composed with F morphism. So these are these diagrams. Okay. So these are satisfying some basic axioms on how the composition of the morphisms work. So you can do this associatively, and there's an identity morphism for every object. Okay, so then so the two axioms are one, morphisms can be composed associatively, so they satisfy the associative property. And secondly, each object to each object is associated an identity morphism. Okay. All right. So before I even go on, where have we seen something like this before? Well, remember that Leibniz had this monadology that he wrote that described monads, and monads were the points, and a monad was like a point taken together with arrows, right, that were emanating from and to the point. Okay, was kind of the description of monads. And so this is related to Leibniz's monads. In fact, so much so this was noticed by so many people that in category theory, um, so category theory has applications. So it has applications to a variety of fields, but one of the fields it has applications to is called functional programming. So in functional programming, these are actually called monads. Okay, so Leibniz's idea of these monads as points taken together in some way with arrows emanating from and to them, it kind of describes basically the underlying structure of a category. Okay. And so Samuel Eilenberg and Saunders Mac Lane in the 40s introduced this specifically for topology, for the purposes of algebraic topology. Now it has been introduced in a ton of fields of math. So the two mathematicians that introduced it, Eilenberg and Mac Lane, wrote a textbook forever ago. I can't even remember. It was probably the first edition was probably published in like the 60s. But it still is, as far as I'm aware, kind of the best way of learning about category theory, and it's called Category Theory for the Working Mathematicians. So category theory for the working mathematician is a really, really good introduction to category theory. And that's by Eilenberg and Mac Lane, who were the two discoverers or first main pushers of category theory. So what does category theory allow us to do? So then we could consider top. Okay, so top, which is the category of all topological spaces. Or maybe the category group, the category of all mathematical groups. So I mentioned group theory before. Here's an example. Here's two examples. A group is also, if you talk about the set of all groups, you couldn't do that under ZFC because the set of all groups, a group is, considering all groups is bigger than considering all sets, because a group is a set taken together with an operation, a binary operation on that set that has certain properties. So a group, considering all groups is even more, that's a larger object than just considering all sets. So the set of all groups would not exist as well, but the category of all groups does. The category of all topological spaces does. Okay. And so it's the morphisms are different here. So the morphisms for groups, the arrows, are what are called group homomorphisms. For topology, the morphisms are continuous functions. Okay, those are your morphisms, continuous functions between topological spaces. Okay, if you consider the category of, say, all smooth manifolds, okay, differentiable manifolds, then the morphisms are smooth maps between the manifolds, right? Infinitely differentiable functions between the manifolds. Okay, and so the reason why I wanted to mention these two first is that we can define functions between categories. These are called functors. Okay, so what is a functor? So here's an example of a functor. So one particular one, we'll call it pi1. Okay, and this goes from the category top to the category group. And so what this means is that I plug in a topological space X, and what gets tossed out or spit out of this is a group G. So pi1 of X is a group G, a mathematical group. Okay, this example that I'm giving is called the fundamental group. Okay. All right. And so, what's an example? Okay. So, let's consider S1, the unit circle in the plane. Okay. There's a standard way of making this a topological space. We can make this a topological space in the sense that it sits inside R2, which has a very familiar topology to us, and we can consider the topology that results from considering this as a subspace. This is called the subspace topology. So consider S1 the unit circle in the plane. So what is this pi 1 of S1? Well, it turns out that if I plug in the circle in the plane to this functor, it spits out a group, which is the integers. I'll explain a little bit in a second. If I let S2 be unit sphere in space, again, I can consider subspace topology here. Pi 1 of S2 is the trivial group. Okay. What is this thing doing? What is going on here? So this particular functor, this fundamental group, has something to do with the number of closed loops on the space. What do I mean by that? Well, if I look at S1, the unit circle, what does that look like in the plane? It looks like this. Imagine a closed loop, right, on this thing. It would be a piece of string that goes around this circle some number of times. Maybe it goes around it once. Maybe it goes around it 3 times. Maybe it goes around it in the other direction 4 times, right? All of those are closed loops. Okay, closed loops and they're loops because they have the same beginning and end point. Okay, so the question is, how many closed loops are there? Well, when we try to count how many, we're allowed to continuously deform any of those loops into any other. But as you quickly see when you try to do this, that it is determined exactly by how many times you went around, either to the left, counterclockwise, or to the right, clockwise, right? So either clockwise or counterclockwise rotations. You tell me how many times you went around, and that is your loop. And there's no other loop that does that on S1. Well, how many of those loops are there? If I went, say, clockwise 3 times, that's -3. If I went clockwise twice, that's -2. Clockwise once, that's -1. If I basically started and stopped here, that's technically a closed loop. That's 0, right? If I went counterclockwise once, that's 1. Counterclockwise twice is 2. Counterclockwise 3 times is 3. Oh. What is that? It's the integers. Okay. Now, let's try the same thing on S2, the sphere. Okay, so here's my sphere. What does a loop on the sphere look like? Well, I start here, I go out a little bit, and then I end up back here. Or maybe I start here, I go around, and then I end up back here. Ah. But I can take these loops and I can continuously deform them, right, through their interior. I can continuously pull these back, shrink these up continuously until they are that point, right? because there's room to pull. I can't do that here because there is no inside of the circle, right? If you try to pull it around that ring, at most you can tighten it up, right, so that it's around that ring. You can't do anything else because you're not allowed to break. You're not allowed to break. Okay, here I don't need to break. I can continuously mush that down to a point. I can continuously mush that down to a point. I can do that for any loop. So how many loops are there on S2? Right? How many of these closed loops are there? There's only one. Any of them can be continuously deformed into any other. Okay. So I can continuously squish these loops to a single point anywhere they are. It doesn't matter. And so that's it. There's none. Right? There's only one. So only one trivial loop, which we can represent as the trivial element of a set. And so going back to what this tells me, I'm spitting out a group here, right? I'm plugging in a topological space, spitting out a group. This is what this has to do. And so you can see now how abstractly, right, coming up with functors and stuff seems weird, but now you see how it arises out of very simple topological considerations, right, why you would want to do this. So if a space satisfies this, that basically any loop is the trivial loop, or can be continuously deformed to the trivial loop, this is called a simply connected space. And simply connected spaces are that's an extremely important condition. Okay. All right. And so anyway, that's that. I think that's a pretty good bookend to see where all of this stuff kind of led in the development of math. So that's it. That is the course. So as I said, I'm still going to post a fourth homework, which won't take you more than a few minutes. It's really just like a brief survey of stuff, and then I'm going to post your exam soon, and I'll let you know when I do. Like I said, you will have access to that exam throughout that window on Thursday, 1:30 to 3:30, and then once you turn that in, that'll be the last thing you have to do for the course, and your grade will be up, a little bit after that. So I'll let you know when the exam is due, but I'll give you a window of a few days that you have to work on it. So, but it shouldn't take you more than 2 hours to do. So that's the deal. So just be paying attention to Elm's announcements, and I'll post all that. So thank you all for the semester, and hopefully I'll see you all in future math classes.